Sure. Yeah. You can just give me a. Oh.
Thank you everyone for coming back after the tea, and we have a few sessions before lunch. The first one is by Ujjwal.
Sorry. Yeah. Hi everyone. Can you hear me? Yeah. Thank you. Yeah. Sorry, I'm going to start coughing while I'm talking, so I apologize in advance. Okay. So hi everyone. I'm Ujjwal Panda. I'm a PhD student at NCRA, and finally, after a long time, I'm going to give a talk about this work I did and published this year on a multi-frequency study of the hyperactive repeater FRB 2024-0114A. So you have heard a lot about this FRB yesterday, and so I won't go to detail into what the FRB is about, but I'll give a very short summary. So this FRB was reported as a repeating FRB by the CHIME collaboration on 26 January 2024. Its hyperactive nature was speculated even in their discovery 18, which is the astronomers telegram. And it was subsequently confirmed by Parks, Muriang, and by FAST when they observed burst storms and a large number of bursts per hour. And then it was subsequently localized by Meerkat and associated with this particular galaxy. It's a bit of a handful, which was a galaxy that was already detected and characterized in the SDSS survey. At the time, because SDSS did not have any spectroscopic redshifts, we only had a photometric redshift of 0.42. Then the localization was confirmed to within 200 milliarc seconds by EVN Precise, which, as you must have heard, France gave talks about this last week. And then we have the host, again, the host galaxy redshift was 0.42, but the spectroscopic redshift turned out to be 0.13, which again highlights the fact that you can't often rely on photometric redshifts. And this was obtained by Mohit and others. And then this corresponds to luminosity distance of 630 megaparsecs. Associated gamma ray radiation was reported and then refuted in a series of ATLs. And there were observations in X-rays, but there was no X-ray emission reported as well from those. And a PRS was successfully associated by Meerkat, by UGMRT, and by the VLBA. And so, sorry, these are our observations that we did. So as soon as the detection was announced, we started doing observations on 25th February. And so these two epochs, we had both phased array and coherently dispersed phased array data. So the phased array data was mostly recorded to actually do the search for the bursts. And the coherently dispersed phased array data was lower number of channels, but higher resolution data that we were eventually going to use to characterize the burst further, get microstructure and things like that. And so we did that in band 4, and then on 14th March, we did a sub-array observation simultaneously in band 3 and band 4. And then after that, we followed up again in July with band 4 with only PA data as well. And so we had a total on-source time of about 18 to 19 hours. And we detected a total of 167 bursts, and with an average burst rate of 10 bursts per hour. So this is a sample plot. Do ignore the submitted, it's already published in AppJ. I forgot to update the slide. But these plots are all available still in my Google Drive. There is also an additional GitHub link, which you can find in the paper, where you have a CSV file with all the burst parameters that you can use. And so you can see, a lot of scattering, a lot of multi-component bursts. This burst, for example, has like 8 components. And you can see, multiple sub-bursts at trombones, things like that. And so this is the Google Drive where all the plots are available. Feel free to ask for the data, and it will be provided upon request. So as part of my analysis, I developed a small package called Scarab, with the intention that eventually the analysis package I'm developing will be used for Spotlight. Again, we have talked about Spotlight a lot this week and last week as well. And so the idea is that it will pre-process the data. We mitigate RFI using IQRM. We then carry out a DM optimization based on a package called Shrine, which is something that the Craft team developed for their FRBs. And then the way we fit can account for scattering and multiple components, which is mostly a profile and a spectrum fit. Those are fit independently. And then we determine, we have a small naive-ish algorithm that can determine the band occupancy of the burst automatically, which you can see here. So it has determined that the burst is only in this part of the band and not in the rest. And then we can only pick the spectrum and the profile for only the part where the burst actually is present in the band. And so we obtain an arrival time, intrinsic width, scattering time scale, and so on for each burst. And so these are the burst statistics that we obtained. We had a large sample of bursts, 167 of them. And so we could see that for our 14th March observations, where we had simultaneous subarrays and we were looking at both band 3 and band 4 simultaneously, there is a wider variation in the structure optimized DM, in the intrinsic width, and in the scattering time scale. We could also see that as we did more and more observations, the flux of the burst started to decline. Now, this flux is obtained using essentially a version of the radiometer equation, where we essentially mimic how the GMRT exposure time calculator operates. And so those flux values, we could see that could show the steady decline, ultimately resulting in a much smaller number of bursts and lower flux in our July observations. And then, of course, we did the waiting time distribution. Again, Chahat's talk, you must have heard the same things. But we could see a very clear gap, which at around 1 second, which have not been seen by others. This could be just because of a lack of bursts. Maybe if we had detected more bursts, this gap could be filled up. But we could we had two distinct distributions in our waiting time. And so because we could see a clear bimodality, we fit them separately instead of fitting them together because it makes no sense. And so what we did was we fit the smaller distribution of smaller waiting times with a Weibull distribution, which gave us the best fit. And we fit the larger waiting time distribution with a log normal because that gave us the best fit. And both of them say that there is some clustering, there's some memory in the mechanism. It's not purely Poissonian. And so, yeah, there's some memory in the emission that is implied by both. Of course, for the waiting time distribution with the smaller waiting times, there is always this issue that we are treating subcomponents as subbursts, and there is no clear way to distinguish between a subcomponent and a subburst, so that it should be taken with like a pinch of salt here. And so then we came to our energy distribution. We first did a completeness analysis following the methodology in Keen and Petrov. And then we got a sample of 91 bursts out of our 167 bursts, which were complete, fluence complete. And then we fit a log normal energy distribution to that because that gave us the best fit. And that shows that at higher energies, we see a flattening despite having a complete sample. So yeah. So then we did a comparison of our waiting time and energy distributions and our burst parameters with other fits done for other hyperactive repeaters. So we have the usual suspects. We have 121102, we have 180916, 201124. All of these FRBs have been talked about this week. And so we saw that a lot of our values of the K parameter the shape parameter for our Weibull distribution and our log normal sigma values matched. A lot of these fits were done, a lot of these waiting time distributions had bimodality, and so they rejected the smaller waiting time distribution with the same caveat that subcomponents and subbursts, they can't distinguish between them. And so that's why our sigma values should match with theirs because we have done the same thing. Okay, so this is my last slide. I'm finishing a bit early. So basically, we continued a campaign on this FRB throughout this year. Once after our July observations, we started our campaign in GTAC cycle 47 in October 2024. And since then, we have detected 126 more bursts from this FRB, making our total now to be about 293 bursts from this source. As you can see a clear evolution. So this is up to our July observation. So these are the bursts that I've talked about in this talk. After that, we see a clear reduction in the burst rate from our October observations, indicating that the emission from the source was probably dying down. And then we see a slow rise in the burst rate. The interesting part is that at first we saw burst only in band 5, which reflects the fact, I think Ajay talked about that in his talk, that the emission was moving to higher frequencies. But then suddenly we saw that the band 4, we started seeing bursts in band 4, which is 550 to 750 megahertz. So that means the emission again began to move to lower frequencies. So that because of which we started to get detections again. And then suddenly there is a shutdown around February and March, which we are going to reconfirm. And then again, the burst switched on again in both bands 4 and band 5. And then suddenly showed a flip where band 4 gave us more detections than band 5, showing that the shift was even more drastic. And then band 5 stopped giving us detections at the very end, and we only have detections from band 4, which shows us that the emission is probably moving around in frequency. It's not just a steady trend towards higher frequencies. And so the entire campaign was spread across 2 GTAC cycles, which gives us about 12 months of data. And so, yeah, this will be published soon. So keep an eye out for my future paper. Thank you.
Oh, Ujjwal.
I'll
I'm sure there are
leave with the
questions.
summary slide. Yeah.
Yeah. Are there questions for Ujjwal? Yeah, please.
Ujjwal, very nice talk. So
Yeah.
I don't have a specific question about this particular observation, but the time gap that you see in between the bursts.
Yeah.
Is it same for all repeating FRBs, or like more or less same, or like very
So
different?
I think it's roughly at the same times as well. So a lot of hyperactive repeaters, I think almost all of the hyperactive repeaters where we have such a large sample that we can fit a waiting time distribution have bimodality, and it is very similar. So even the peaks
bimodality
are
is
at
similar, but the time gap that I'm seeing here.
No, the time gap, okay, again, for this FRB, for example, if you saw Laura's talk, she reported there was no time gap. So we are not sure if we add more bursts, this could get filled up. But the bimodality is seen in all of them. The time gap, it may not
I'm
necessarily be
interested
there.
in the things where there is nothing. But
Yeah,
you can just find the difference between the peaks. Okay.
Sorry,
I can just find the difference between the peaks.
Yeah.
That let's call that as a different time gap.
Yeah.
So
So that time gap must be similar. Yeah. So that is often, even the peaks are often at similar times, and the distributions are at similar time scales. So people often see one distribution at very similar millisecond time scales, and then another distribution at a few second time scales. Often the peaks are at similar values. So that is something that is seen across a lot of
very
hyperactive repeaters.
Yeah. And also so you correct for the redshift, right? Not the redshift time delay, 1 plus Z.
In the waiting time distribution, I don't think I did a redshift correction here, because again, the assumption is that they're all coming from the same redshift. So I shouldn't need to. For the comparison, yes, yeah. Although I don't know whether other people correct as well. I have a bit of a doubt there whether other waiting time distributions they correct for the redshift. So their comparisons might be a bit, for sure,
Sorry, questions?
Oh, hi, Ujjwal. Nice talk. Can you move to the last slide?
This one?
The very last, the summary thing.
Okay, the summary.
Yeah, the last point where you're talking about temporal and frequency dependent evolution. Are you gonna push a theory that there is a plasma lens in front of it? That's why you see a sudden evolution and the sudden magnification in a certain frequency area, the amplification, probably because of presence of plasma lens in front of it?
I could. I would like to have a look at all of the data first. So I have like 2 more epochs to analyze, and I have to collect all of the bursts and see. But yeah, that could be one of the theories, because we are seeing not just a trend, not just a simple trend. You're seeing that it moves back to low frequencies, then moves back again to high frequencies. So it's kind of moving all over the place. It could be something like plasma lensing for all.
Yeah, because my comment comes from the talk of Ajay, and he was even showing the, I'll say, spectral evolution and also the burst rate as it going up and down, up and down.
Yeah.
Probably if you could model a plasma lens.
Yeah, it's possible, because as far as I remember, the host GM is quite large, and there is a PRS associated as well. So there is always a possibility that because there is a lot of plasma around the host, that there is plasma lensing effects that are happening. Yeah, it's possible. But again, I would like to look at my data a bit more thoroughly first, because this data is just from a simple search that I've done till now. I just have searched for the bursts and I have them, but I have to look at the data to be very sure. Yeah.
Thank you.
This one.
Hi. Just one quick comment. The right peak in the weight time distribution, the position of it is just 1 over the rate of bursts that you see. So if you would see a higher rate, they would probably get closer and overlap.
I'm sorry, you're saying that the gap will get, no, I didn't get
Yeah,
you.
so the right peak reflects your rate of FRBs, the position of the right peak. So it would come closer if you saw a higher rate.
Yeah.
But my actual question was about, you said that the log normal is fitting the right peak better.
Yeah.
What kind of model comparison did you do there?
Oh, so I fit, if I remember correctly, a log normal, exponential. I think power law fits as well. I think a gamma distribution and a few others, I think. So I tried a lot of them, and the log normal was the best fit among all of those. So I basically I fit what would have been. So it would, the waiting time distribution is exponential for a Poissonian distribution. So the exponential did not give me a good fit, which told me that this is not supposed to be Poissonian, but and the log normal gave me a much better fit. So that's why I went for the log normal. Yeah, but I did like a comparison for a lot of distributions. Yeah.
We have time for 1 or 2 quick questions. Ujjwal, I'll have a question.
Sure, yeah.
So are there any simultaneous observation by other observatories and or higher frequencies? Do they report anything?
Well, not that I know of, but again, the data set has been made public. So if somebody informs me, yeah, but I didn't do any simultaneous observations as of now. This is a purely GMRT based campaign. But if there is a chance that, for example, from either the old data set, for which the information is public, or the new data set for which the information will become public once I publish, if there are any simultaneous observations that I don't know of, I would be happy to check and see whether there are any simultaneous bursts at higher frequencies, for example. Yeah. Yeah, 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 yeah. Yeah, for the FRB itself, there are, of course, yeah, simultaneous observations. Yeah.
Yeah.
Yeah, sure. I'm sorry, I'm not sure whether okay, a pattern in all of the bands changing here, that's what I don't think so, because it has been a bit, so yeah, I know. Well, so okay, yeah, for 180916 there has been a clear pattern, but that is like an exception. Most have not shown a clear pattern in which frequencies they would emit at preferentially. It was 180916 which was emitting more in low frequencies than higher frequencies, so there was a clear chromatic evolution of its emission activity. But what we are seeing here is a bit random, so it does not match with anything that's happening there. There was, again, as Ajay mentioned in his talk, there was a chance that it was following a completely opposite trend. But from what I can see in my data, it's not holding up. So yeah, might just be random. Yeah, but 180916 is the only FRB. There's no other hyperactive repeating, which shows a clear trend in chromatic trend in activity. Yeah.
Any other questions? Any polarimetric observations? Polarimetric analysis on the data?
Oh, so I do have some polarimetric data for this, but we will see how it goes. But the campaign kind of shifted its focus to studying the emission activity exclusively. So I don't have polarimetric data for what everybody would like for this very active epochs or the active epochs. So yeah, I won't be able to do it. But yeah, again, I think others are doing good polarimetric analysis with both GMRT and other telescope data. So yeah.
Thank you.
Yeah.
Yeah, please catch Ujjwal again. If you have some question comes up in your mind. So we'll move on to Resmi. Sorry, Arvind.
Yeah. So first you keep. Yeah.
Yeah, hope you all can hear me. I thank the organizers for this opportunity to present my work. So I'll be talking about the nature of the persistent radio source associated with one of the well-studied repeating events, the second known repeater. So over the past few days, we have all talked a lot about FRBs. So I just thought I'll summarize some things here. So I might go a little quicker here. So yeah, the origin of FRBs is still an open question. There are different models that have been proposed. There are a cartoon of a few of the models here. There are very exotic models like this to explain some of the repeating FRBs. There are some models which talk about mergers, and if so, the observations of FRBs itself have given us these kind of sources. So there are repeaters and there are apparently one-off events. We don't know if these one-off events will repeat later in the future. So if so there is this question of if there are actually different populations. So if there are separate one-off events, then mergers can also cause them because these are catastrophic events. Again, there's this question of if there are different progenitor mechanisms itself for within each of these populations or as the FRB population as a whole. So there is this catalog of the possible models here called FRB theory cat. So you can just go there and look at it. There are a lot of different models. So to understand what FRBs are, we have again talked about this in the last few days. So I just thought I'll break this down into two things. So to understand FRBs, we need to localize them and then we need to follow up. So to localize them, we have already seen that there are new instruments, new commensal systems that are looking for FRBs and trying to localize them to smaller regions in the sky. Once we have them localized, then we can think about looking at the electromagnetic signatures from these events. So we can look at the environments in which they are, look at the intervening medium between them and us, and then try to understand what causes these FRBs. So we have also talked about, I mean, there were very good talks about host studies. So yeah, looking at where these sources are within the host galaxy can give us some idea about what they are. Again, we have to look for counterparts. So if we have really good localizations, we can start cross-matching with other known transients or other wavelength surveys to look for any counterpart emission that could come from these sources. We know only, I think, one such event of the galactic magnetar, which showed X-ray bursts along with the FRB-like bursts. Then we can look at this thing called persistent emission. So what is this persistent emission? I'll just go to that. So some of these FRBs, a very, very small fraction of these FRBs have been seen to show persistent radio emission. So I'll just get to that in 1 second, but by handful, I mean 5 of them. So there is one very recently discovered one, which is in Alexander's paper, which came out very recently. So I suggest all of you to just look at this paper. It's a very nice paper, which gives our current understanding of all PRSs and I mean FRBs in general. So it's a nice paper to look at. So this is what they reported the discovery of a persistent radio source, which is associated with this particular FRB. So there are five FRBs which have been shown to show this persistent radio emission. All of these are repeating FRBs. So again, we don't know if the apparently one-off events actually have any persistent radio emission. What we mean by persistent radio emission is continuous radio emission. On top of the burst-like emission that we see from these repeaters, we also see a continuum radio emission, which is active for a very long period of time. So many of these have been studied for a long time. So if you see 121102, the first repeater that was discovered, it has been, the repeating bursts have been studied for a very long time, and we have observations of the persistent radio emission for the last 6, 7, 8 years. Then we have 190520, also which has observations for the last five years. The persistent radio emission has observations for the last 5 years. So the characteristic of these persistent radio sources is that they are really bright in the radio. You can see the radio luminosities here. They also have a very shallow spectral index. So you can look at the spectral index that is above these frequency bands that are listed here. Then all of these persistent radio sources also had EVN observations to actually localize them better. So the EVN campaigns were also to localize the bursts. So we have strong constraints on the physical size of almost all of these persistent radio sources. We also have constraints on the offset between the distance between the locations of the bursts and the persistent radio emission itself. So except for this one persistent radio source, most of these persistent radio sources have very small physical size, and they are also very, very close to the FRBs that the burst source itself. So this actually gives us an idea about the possibility that the persistent radio emission and the burst emission are coming from the same physical source, or from the immediate vicinity of the physical source that is producing the burst itself. So given the persistent radio emission for these, I'll just discuss a few possible models that have been used to describe both the burst and the persistent emission. I mean, this is not an exhaustive list. I'm just trying to give an idea of some of the models. So the first model here, so I mean, given the detection of the X-ray and X-ray bursts and the FRB-like emission from the galactic magnetar, we know that at least some FRBs may originate from magnetars itself. So there is this model called the magnetar wind nebula. So where like after a massive star undergoes supernova, there is a supernova ejecta, and it leaves behind an active magnetar. The activity of this magnetar actually inflates a nebula within the supernova ejecta itself. The activity, the FRB comes from the shock of the shocks that generate the activity, whereas the persistent radio emission comes from the nebula here. So there are electrons here in the magnetic field which are producing the persistent radio emission. We see the RM itself, the change in the rotation measure, also due to the ions present here in the ions and the magnetic field present here in the nebula, and the DM itself comes from the ISM and the medium towards us. So this is one model. There is another model called the hypernebula model, where we have a compact object which is accreting onto itself from another companion. The companion is not shown here. The accretion itself might cause production of FRB-like emission from the source, whereas it also starts to emit a wind-like emission from a slow wind-like emission, which will interact with the interstellar medium and start producing the persistent emission that we are seeing. So yeah, these are the two major models that we actually talk about when we are looking at persistent radio sources. There are other models also, but now I'll just go on to talk about the persistent radio source that of interest that I'm going to talk about right now. So FRB 190520 was actually discovered by FAST and was localized to a dwarf high star forming galaxy. This FRB itself also had EVN observations, VLBI observations, which actually showed the presence of a compact PRS. So this is the image of the persistent radio source. The spectrum for the PRS actually resembled 121102 at frequencies greater than 1 gigahertz. There were lack of low frequency observations of this source. So what we did is we compiled long-term both UJMRT and VLA data to study both temporal and spectral evolution of the source. So just before I go to our data, up to 2021, this source was also extensively studied by other groups with VLA. So this is a plot of the spectrum. The different colors here are the different epochs. So in this study by Zhang, they have actually shown that from the 2020 epoch to the 2021 epoch, they had seen a slow overall decay in the flux in all frequency bands. So what we did was we took GMRT and VLA observations along with some of the archival observations for this persistent radio source, and we compiled them here up to 4 years after its first observation. So what we see here, the main thing that we have to see here is the light blue color, this one, which is 1.5 gigahertz, which combines both VLA and GMRT observations. We do see some evidence of the source brightening and dimming on timescales of like a week here. I'll talk about that a little later. So to look if there are trends, monotonic trends in the data itself, what I did was that I scaled all the data to 1.5 gigahertz using a spectral index, changing the spectral index to, I used the spectral index here at the end of 2021 epoch, but changing that to any of the other values doesn't change it much. So if we do a statistical test for monotonic trends called the Maan-Kendall test, I won't go into the details, but it tells us if there are if there's a monotonic decrease, increase, or no change in the in a data set. So we did find a decreasing trend, and I show the linear regression that shows a decreasing trend here. There is, however, this brightening and dimming, which I'll just talk about in like 2 or 3 slides from now. So yeah, given the dimming, what we did was we tried to look at any physical constraints that we could try and obtain. So the Magnetar Wind Nebula model that I talked about, we tried to give a joint, make a joint time and frequency fit for all the data that we have till now. And so here I'm just showing the time, the light curve as a function, the flux density as a function of time, and for the different colors are the different frequencies. So this is the joint fit of the Magnetar Wind Nebula model. So given the Magnetar Wind Nebula model, we can actually get constraints on the age of the Magnetar, the energy injection from the Magnetar itself, the rate of energy injection from the Magnetar. So yeah, we were able to actually constrain the age of the Magnetar to around 52 years. This is slightly higher than the estimates from the other fits till now, but it still sits within the allowed parameter space. I'll just come to the parameter space in a second. For the hypernebula model itself, there were already fits from previous studies, and at these timescales and from the observations of the bursts itself. So the hypernebula model actually predicts some variation in the DM of the bursts itself over time. There are slightly contrasting things about this source. So there have been studies of DM of the bursts itself, and initially it seems to be showing not enough variation. But there are also some studies which have shown a slow decrease in the DM over time. For the spectral fit itself, so the same joint fit that we did in the previous slide, I've shown here on the spectrum though. And the different colors here now represent the different epochs. So what we can pay attention to here is the GMRT low frequency data, the data that is below 1.5 gigahertz. So we didn't have many observations of this source in this frequency band. So our observations actually show that there is a possible absorption process that is taking place here, and over different epochs we still see the absorption happening. Unfortunately, we didn't get detection, so we cannot give quantitative estimates of what the absorption is doing over there. But this again suggests that this source is actually in a very very dense environment. So yeah, if you just go back a few slides, we did see this this variation in the flux density itself. So for frequencies above 1.5 gigahertz, sorry. Yeah, for frequencies above 1.5 gigahertz, there were already studies done on the variability itself. And there has been some evidence for variability in the 3 gigahertz. So what we did was we took only the 1.5 gigahertz data and we looked at the possible variability. So one of the possible reasons for a variation in the flux that we see is scintillation. So as we had already talked about, PRSs have are very small objects, so have a very compact size, and so they can actually have this thing called scintillation. So it's like a radio twinkling. From our observed data, we were able to calculate the modulation, and from the modulation, we can actually place. We don't get as much modulation as expected from scintillation in this direction, but we have tried fitting for the entire data, or also tried removing this this decay trend and looked at scintillation, and we are able to give some constraints like a conservative lower limit on the size of a scintillation screen that can be at different distances at like 0.1 kiloparsec, at 1 kiloparsec, or 10 kiloparsecs. And these lower limits sit within the limits that are already present, which was actually discussed in this paper. So yeah, with that, I'll just give a summary and I'll take any questions.
Thank you. Any questions, please? Ish.
You showed the GMRT upper limits.
Yes.
Could you point the 1 gigahertz point, which ones would be like closer to the epochs? If one has to connect the spectrum.
Yes.
And these are multi-epoch points, right?
Yes. Yeah. So actually, so we had GMRT. So GMRT follow from I think from here. So all of these points are GMRT 1.5 gigahertz.
Yeah, in the spectrum, I mean.
In the
next slide, yeah.
In the spectrum, it's slightly hard to see. So just a second. So I'll just go here. So 2 years since, this is 2.5 years since observation. So that is like 2021. So from the 2020 epochs, which have these points, the hexagonal points, all of these later at 1.5 gigahertz. So all of these at 1.5 gigahertz with the hexagon star, and these are the points.
Okay, the kind of steep turnover you see, is it still consistent with free absorption or synchrotron self-absorption?
Yeah, actually, I was trying to look at that, but the problem is that since we don't have actual detections, we cannot exactly say what this one is. We can maybe plot a slope for the free or the synchrotron self-absorption and check that. But yeah, quantitatively, I haven't estimated whether it is free or.
Hi, Arvind. So my question is regarding constraining the size of the PRS, and if that, what are the constraints we can put on different models based on that?
Yeah, so I mean, yes, once we constrain the size of the PRS, I guess we can say if it is the immediate vicinity. So I mean, there are estimates, at least for say these two models, there are estimates of the the size that this nebula can inflate to, the size that given module or the other parameters, you can get the size of this nebula or the size of the this cloud that it can this central object can inflate. And so if we get in similar sizes, if the constraints are agreeing with that, then we can make some statements about these models. So that was the idea.
So thank you, and I'm sure more questions we'll address during the break. Thank you very much again. And now we are moving on.
Am I audible? Okay. Yeah. So it's sorry. Change slides. Right. So this is a semi-outsider's review of gravitational wave FRB connection. My engagement with the FRB community was my study of the persistent radio counterpart, which the first one, which Arvind presented before he took over with the GMRT, a study that we presented, we did with my collaborators, Rakovink and Ishwar Chandra. But I have a strong interest in multi-messenger astronomy, which is mainly due to my association of gamma-ray burst physics. So this is in this background that why I said it is a semi-outsider, because I haven't really gone into FRB studies with working out FRB connection with gravitational waves, but until now. So, but maybe this is a beginning. Thanks to Jayanta for asking me to give this talk. So what is multi-messenger astronomy? We have so far known at least so far 4 messengers through using which the universe speaks to us: electromagnetic radiation, cosmic rays, neutrinos, and gravitational waves, in this order to a good extent. So these are at least the 4 known messengers that we have. And gravitational waves officially became the messenger in 2015, when the first gravitational wave source was observed with the advanced LIGO-Virgo detectors, which was the merger of 2 black holes of 36 and 29 solar masses at more than 400 megaparsec from us. This signal we see here is a sketch of the numerical relativity signal and reconstructed template of the merger of two black holes. The black holes initially show an in-spiraling phase. They come closer and merge and ring the phase of ring down after the merger. All these four phases, all the phases are shown here, where we can see that the time and the frequency, as time goes on, the frequency is going up. And in another way of presenting this, one can also see the amplitude of the signal will go up and will peak around the merger. So both the frequency, which is a representation, which sort of connected to the orbital frequency of the components. Both the frequency and the amplitude will intuitively, one can see that it will go up and reach the peak towards the merger. So since then, the LIGO-Virgo-Kagra interferometer network has detected several binary black holes, binary neutron stars, and neutron star black hole mergers. These are all bursting transient events. Here is a very older version of the LIGO-Virgo-Kagra catalog of gravitational wave transient events. What I just now mentioned, that the amplitude going up can be seen with this color scheme here. And on the frequency, this y-axis is the frequency and the x-axis is the time. Then you can see that the transient signal, as it starts coming from here, peaks here as the merger occurs. So these are different type of, this is the merging two neutron stars, and there are also merging black holes. LIGO has, like LVK has also seen merging neutron stars and black holes. This is also another very famous picture, a sketch of the masses in the stellar graveyard, what kind of compact binary coalescence has LVK has so far seen. This is the most recent one. So you can basically see how the masses are all, I mean, what sort of events are merged. So for example, you can see two masses merging and becoming a third mass. So this entire picture is something which you can go and check later. We will not go much into this. What about other type of sources? LVK has so far only seen this merging coalescing compact binaries or CBCs. This depends, why don't, the fact that we are only seeing these type of sources is because, not because other sources cannot emit gravitational waves, but because because we have this ground-based interferometer network, and the gravitational wave detectors work by looking at the changes in the interferometer fringes as when the space-time is, when a gravitational wave passes through the interferometers. So it depends on the length of the arms. So of course, when in future, so this is just an animation of how the interferometers work, and this as the gravitational wave passes through. So definitely the fringe changes in the fringe of the interferometer, which is later decoded as the gravitational wave signal. How much can you, what sort of frequencies you can probe will depend on the antenna length. So this is why in future, when the laser interferometer space antenna, where the interferometer arms can be much, much longer because the interferometer will be in the space, we can really see other kind of sources, say, for example, white dwarf binaries, coalescing supermassive black holes, neutron star stellar mass black hole. Many of these probably, one doesn't know whether these sort of sources may have something to do with FRBs. That's why I brought it here. So the summary is that right now we see CBCs in gravitational wave detectors, but in future we can also see other sort of sources. Well, so this was all about just the gravitational wave detection. What about multi-messenger astronomy? Multi-messenger astronomy is when we are able to see two messengers. Here in this talk, I'm focusing on gravitational wave and electromagnetic radiation. The two messengers from the same phenomena, which will improve our understanding of the physical process in several dimensions, because the two messengers will be coming from two different parts of the source. So they'll be complementary. They'll actually be arising from different physical processes, one from the gravitational interaction, the other from the electromagnetic interaction. So here is the first and only one in multi-messenger astronomy signal in GWEM that we are so far aware of, which is the merger of two neutron stars. This is the chirped signal, the similar thing that I had shown earlier, where the frequency and time goes up at the time of the merger. And this is what the LIGO-Virgo observators, LIGO-Virgo detectors have seen. And what made this event, of course, interesting is, of course, the electromagnetic signal temporally and spatially associated with this in the form of a burst of gamma rays. Which we can see that the time of merger, soon after that, around 1.7 seconds later, there is a burst of gamma rays detected by the Fermi Gamma Ray Space Observatory and the Integral Gamma Ray Observatory. This is also spatially coincident, which which confirmed a well-known hypothesis that this class of burst of gamma rays called gamma ray bursts are associated with merging neutron stars. And not only that, this event was much more important. It was one of the most significant event in the entire history of recent astronomy, that this source was also seen in other wavelengths like radio, X-ray, optical, and optical near IR, UV, etc. These are two different type of sources. One, following the binary neutron star merger, there is a jet that is producing the gamma rays, which further produces X-ray and radio emission. And there is also a source called kilonova, which produces most of this optical IR UV emission. So you have actually two electromagnetic sources. One is the gamma ray burst, and the other is actually three, because one is the gamma ray burst, the other is the afterglow, which is seen in X-ray and radio, and the third one is the kilonova, associated with one type of gravitational wave sources. This is a golden multi-messenger astronomy scenario. Unfortunately, we have just this one. And this is where our work also comes in, because we also joined in this. We observed this the source with GMRT, and there are several other teams which observe the same source. So I'm just only writing our collaboration's name. So of course, this has led to a lot of deep understanding in the in our idea of both gamma ray burst and binary neutron star mergers. The kilonova, which I mentioned, was the first time being detected. So now going ahead to, is it possible to have such groundbreaking discovery with FRBs? Can we see fast radio bursts associated with gravitational wave signals or vice versa? It's a very difficult question at the moment. So there will be a session. I mean, I think I understand that there will be two sessions on Thursday and Friday about FRB sources. What kind of sources can produce FRB signals? So as I said, this is just a very, very brief overview of this. I am based mostly by this excellent review article by Bing Zhang in 2024. So let's say even if we consider independent of whether there are all the repeaters are really, all the non-repeaters are really non-repeaters, or are they repeating FRBs with a very long wait time, we can definitely, there are two types of sources that have been discussed in the FRB literature. The ones that can power, the sources that does not end with the production of an FRB, which is required for repeating FRBs, and the other kind which is the result of a cataclysmic event. In both cases, the magnetars are a favorite candidate. So most of these models involve magnetars tapping their magnetic energy reservoir and producing FRBs. There are models which are based on pulsars, giant pulses, or interacting neutron star systems where the spin or gravitational energy is being used up to produce the radio burst. In the cataclysmic models, the most favorite model is of combat binary coalescence. There are also other models called blitzers, where there is a neutron star ejecting its magnetosphere when it implodes as a result of perhaps a merger, or perhaps its rotational angular momentum can no longer support it. So here are some small numbers of these models. Here is, so what sort of scenario is there? The BNS mergers normally produce, as I mentioned earlier, for 1708, 17 also. It's a very messy environment with a tidal ejecta, that is neutron-rich tidal ejecta produced from the merger, because both the neutron stars gets ripped apart, and also possibly a jet. So there is, of course, a question that even if there is an FRB signal that gets produced, is it possible to escape this messy environment? Another possibility is that the signal, FRB signal is produced before or after the merger. So such models are, one of which is a unipolar inductor model, where the weakly magnetized neutron star has two neutron stars in spiral and well before their merging phase, then weakly magnetized neutron star will be going through the, crossing the stronger magnetic field of the other neutron star. This is the sort of model which was proposed for Jupiter and its moons system. And the calculations sort of show that it can produce a luminosity of something like 10⁴ per second for this sort of magnetic field and the separation between the two stars, which this, we can actually see that this is very close to the merger with a separation of 30 kilometers. Another kind of physical model is the classical theory of radiation, that the accelerated charges radiate. So you have a charged CBC companion, which is a neutron star in the compact binary, which is having a charge, global charge. As it accelerates, as it as it orbits around its companion in the common center of mass, it accelerates, and dipole radiation and both the electric and magnetic radiation can be produced. And this sort of calculations show something like 10⁴ ergs per second or so. Both are the sort of energies that we see in FRBs. The before merger scenario has the sort of, as I mentioned earlier, if the FRB emission can come before the merger, then there are also models where magnetic reconnection in the interacting magnetosphere that produces repeating FRBs. One good thing is the matching with the luminosity and also the potential for LISA detection, because LISA is possible, can possibly detect inspiraling combat objects before they merge well before decades or centuries before the merger itself. What about the after merger? The post-merger, if there are two neutron stars, you can either form a long-lived supramassive neutron star or a stable neutron star or a black hole, depending on the equation of state of the neutron star and the mass of the components. If you have a supramassive neutron star, as I mentioned earlier in the Blitzar models, it can eject the magnetosphere when it collapses to black hole after after living for some point of time. And this could lead to an FRB-like event. If there is a stable neutron star, perhaps if the magnetic field is high, probably repeating FRBs could be produced. In case of neutron star black hole mergers, there are two types of course, the end products will be a black hole, so a repeating FRB is impossible from such a scenario. But I mean, a post-merger repeating FRB system is impossible. But NSBH mergers are two different types. In one type, depending on the mass ratio and the spin of the black hole, it could either disrupt the neutron star when there is the material that is around the system, or it could just swallow the neutron star. Depending on these cases, there are there are different suggestions or proposals. I will not go more into details of these. So this is just a summary of everything that I mentioned, but because there isn't much time in hand, I'll just go ahead in the searches that people have conducted so far. There have been searches of gravitational wave signals in O3A, several associated with the chime FRBs, and they haven't, of course, found any significant evidence. However, having no significant evidence for association does not mean that you can exclude GW association. So using the volumetric rates of BBH and NSBH and BNS and FRBs, the conclusion that the paper has arrived at is that at most 15% of FRBs could possibly associated with BNS mergers and 1% with NSBH. This conclusion is based on this huge difference that we can see between the volumetric rates of FRBs and NSBH and BNS systems. There was a GEO 600 search for the galactic SGR FRB during it occurred at a time when LVK was not operational, it was temporarily halted. At that point, there was a search by the GEO 600 instrument, but not anything was discovered. There was also a putative association of an FRB and a BNS merger, which was this, of GW 190425 and FRB 2019-0425A, which is somewhat, this FRB, which was detected in chime in 400 to 800 megahertz band, 2.5 hours after the BNS merger. The DM distance was consistent with the GW distance posterior, This is the FRB, and this colored map is the GW localization posterior. So there was also a hint of a gamma ray excess by the integral mission. However, we have Mohit Bharadwaj's work, which argues that there is an unlikely possibility of an association, which depends on the viewing angle and the present need of having a clean space for the FRB signals to go on. However, this is one important event. And the second one and last one is this: a low-far coherent source associated with a gamma ray burst, the kind of gamma ray burst that is expected to be produced by the merger of two neutron star or a neutron star black hole system. This again, so such coherent radio pulses are proposed, hypothesis to be associated with compact binary coalescence. So LOFAR seem to have seen something like this, but it is sort of also a sort of weak association. Nothing conclusive could be said at this point of time. But if it is truly associated, it is a case of post-merger FRB emission, because the coherent radio emission is around 5.6, about 76 minutes after the short GRB. But this was a very low significance event as far as I know, so not much of the radio signal properties are clear to me. So with this, I'm stopping here. And
thank you, Rashmi. We have time for a little one or two questions, quick questions.
Thank you for the talk. I have a very naive question. So we all know that FRB's positional uncertainty is very small compared to the positional uncertainty of a GW event. So how can one overcome these kind of difficulties to figure out any association between FRBs and GW events?
So what was the beginning? I missed the word.
So the positional uncertainty, the error in RA and DEC.
Okay, yeah. So one, see, the problem more with GW FRB localization uncertainty, gamma ray bursts are reasonably better localized thanks to, so for example, in the LOFAR case also, the localization of the, I didn't explain that, the localization of the gamma ray burst signal was much better. Gravitational wave and FRB association does suffer from this problem, that both, if it is I mean, I understand that the chime localization has improved drastically now, but gravitational wave localization capabilities are still not very high unless LIGO India probably comes up and improves this. So definitely there is an association issue. And maybe an escape from all this is probably another kind of electromagnetic signal, maybe in X-rays or radio waves, which can be a more like for example in 1708-17, the longer lasting radio emission could actually be used to pinpoint the location or optical signal. If we have that, that will be better.
Any other short, quick questions? Yeah, one.
So generally the uncertainty in when you calculate the rates for the say the mergers, that is pretty high. So if you just factor that in, will it be consistent with the FRB rates, or how will it change?
Did you mean this number? This number? Is this what you meant?
Yeah, you can see here also the rates are very have a wide range.
Yeah, but still the FRB rate, this is the rate of volumetric rate of FRBs with luminosity larger than 10⁻42 per second. That is still actually much larger, right? In comparison with the BNS rates are actually in fact gone down. I don't remember which number this is from. I think GWTC3, TC4 actually we haven't had much BNS mergers, so we have actually gone down. So I think it's going in the other way around. Maybe the only option is to say that the even more luminous FRBs are probably only associated with. I mean, that's one option.
Thanks.
Jayanta.
So Rashmi, when you like in this slide, when you talk about 15% of the FRB could have double neutron star, binary neutron star merger association. So is this considering the post-merger scenario, or is it pre-merger, or is combined both?
Okay, so this is just the search of GW signals, 3 associated with chime FRBs. They were just checking for temporal and spatial coincidence of a GW signal with chime at that time. I think chime has a much larger error region. So mainly maybe all they were checking for a temporal coincidence to within whatever error region that you can have. And they found no association, which does not rule out so then all that they can say is the maximum is this, that. Yeah, so it was just, probably it is not, I mean, you cannot really say, yeah, for that I need to see how much range of time did they scan, which that number I don't have in mind. Compared to the child time versus the GW search window is something I don't have in mind. But probably it will include at least post-merger and at the time of merger, because pre-merger may be a little too difficult actually with this GW instruments.
Rashmi, then next slide where you were showing the GW.
Okay. Which one?
It could be said as a precursor to. Is there anything that you could say here?
No, sorry.
Which one?
Happened first. So BNS merger is first, then 2.5 hours later, the FRB. So this will be something like a post-merger. This will be a post-merger, actually. But this was, I think, the work of Mohit Bharadwaj. I mean, they're really questioning whether there could be any association.
Okay, thank you. I'm sure more questions, and Rashmi.
This one. Yeah, so I am working with Vikram at IIT Tirupati with Vishal and my collaborators shown here under the SETI Technosignature grant. And Vikram has already given you an idea about what I'm going to talk about. But before moving on, I would like to mention two members, Shambhavi Jaiswal and Ibrahim Matthews, who have contributed a lot to building the machine learning model and coming up with training methodologies. So moving on, this is what I'm going to discuss. I'll just start with brief introduction of exoplanet discoveries and then move on to the work that we have been doing. All right. So yes, so without this question, just like an FRB repeater, I have to keep repeating this question probably until we actually find an answer as yes. So moving on. So what the question from are we alone to seeing how far we have come or how close we are still to finding answer to that question. So the purpose of showing you this slide is to give you an idea of how many exoplanets have been discovered And there are like close to 6,000 now. And maximum number, around like 3/4 of them are coming from transit method studies. And what has emerged is the variety of the population of exoplanets that have come out, with rocky planets and ocean worlds occupying a large fraction of these discoveries. So what makes us hopeful is the existence of these Earth-like planets, which are probably very similar in terms of the nature of their surfaces. So we are very hopeful of finding either a biosignature or technosignature detection in one of these exoplanets. So our hopes are very high, and my belief to the question is that, of course not, and probably many of you will agree with me. So let's just move on to the next slide. Because transit method have contributed to a large fraction of discoveries, I just want to briefly introduce, in case you don't know what transit method is, which is just basically, not sure how to play. Sorry. Okay. So as you, any planet that is going around its star, if you keep looking at the star, then you will see, as a function of time, the stellar light keeps varying, and you will see periodic dips in the stellar light curve. This is what is referred to as light curve. And these periodic dips are the indication of presence of a transiting system. So transit missions like Kepler mission, which has already been completed, that I'm going to talk about more in detail later, and the TESS, which is Transiting Exoplanet Survey Satellite, and the upcoming Plato, are going to contribute a lot to the sample of light curves. So the question is, how can we use these light curves for our technosignature search or not? So what we know from these light curves is that the ingress and egress, which means when the planet enters the transit and when it exits the transit, has imprints of the shape of the transiting system. So this is our aim, that we want to image the shadow or the 2D projected image of the transiting system from its light curve. So yes, so moving on, I'll just mention quickly the Kepler mission, which has been the NASA's planet hunter, and it has looked around 150,000 stars in our Milky Way galaxy. And what it did is to look at a very fixed patch of sky continuously for 4 years. And to give you a perspective of what it did, such deep observations, I'll just show you a cartoon picture. It's not as nice as other animations that you may have seen, but it'll give you an idea that if you take if this is sun, then there is a planet, Jupiter, sitting at the center, which is 10% the size of the sun. And you may be able to see, I'm not sure, a tiny dot at the center, which is like Earth, which is even smaller, which is only 1% of the size of the sun. So the question is, if we try to, so if we try to I just try to zoom in to show you, to be able to see these tiny planets there, then you will see that the Jupiter, if Jupiter is orbiting the star, you will see only 1% change in the light curve or the depth of the star. Whereas if you look at Earth-like planet, it will be even smaller, like much smaller to detect by any ground-based telescopes. So what Kepler has achieved is this unprecedented depth, close to 20 parts per million, which is in principle able to detect even planets half the size of Earth. So that is in some sense, the revolution of the Kepler, and it has so far contributed to close to 3,000 exoplanet discoveries alone using this method. And there are like 1,000 to 2,000 still waiting to be confirmed. So we want to use this large amount of transit light curves to do our study. All right. So yes, this is the aim. We want to find anomalous transiting shapes. So what does it mean? So I'll just give you quickly the idea. Let's say for the timing, we know what are the shapes of the transiting systems. And we also can find what is the corresponding light curve that one observes from these stars. So then what we want to do is to take this as a labeled input data set. So shapes and the corresponding light curves. And we want to build a machine learning model to be able to, which is here, to be able to tell us what the shapes of these transiting systems are. And later quantify them as whether they are a part of normal planets, which will give us roughly the circular shape, or whether they are something different from planets or some weird shape. So this is the idea. This is the whole picture of what we are trying to do. And how this will contribute to technosignature is what Vikram has already mentioned, that the Dyson disks are something that one can look for, the weird shapes that we will look for, which will be the best candidates for technosignature searches. Okay, and given the large amount of data, a machine learning approach is going to be best suited to do this kind of study. Okay, so the step one is to get these variety of shapes to be able to train, to be able to give it to the model, machine learning model. So what we have done is to generate all kinds of shapes, from circles, ellipses, symmetric shapes to weird shapes. And this forms the sample of the shapes. So now we have also rotated the shapes to increase the number of samples. And the next step is to actually find the corresponding light curve. So to do that, what we have used for the time being is the 8-bit transit package. What it does is, if you have a grid, which is basically an opacity map with the values between 0 and 1, and you just make it pass across your star, it calculates how much of light you will receive from this star, given that these black pixels would be blocking some of the light while transiting the star. So this is, we are using this, and you can find this paper link here. So just to mention that we are not using the UT code that Vikram mentioned earlier, because it is computationally very expensive. So for the timing, this is what we are using to generate the light curves for given shapes. Okay. So yes, this is our training model. It's a simple convolutional neural network, which is not very deep, and the input is the light curve. So we have standardized all the light curves to be between 0 and 1. So depth is 1. And also the transit is such that it is always at the center of our input light curve with 120 points in total. All right, so I'll just explain what assumptions, under what assumptions we are generating the light curves. So we have assumed that the impact parameter is 0, which means the planet always transits mid-plane with respect to the star and with respect to the observer. And the transiting body does not rotate about its own axis. And there is only single structure at a time that we are trying to model. And we have also included the limb darkening model for the star. Okay, so the very first results that we want to show is the predictions on the test data. So on top of that, on top of the light curve, we have also added Gaussian noise after scaling. And we want to then just give these test light curves to the machine learning model and see what it predicts, what shape it gives us compared to the ground truth. So you can see in this figure, the ground truth is shown in the rightmost column, and the predicted shapes are shown in the corresponding row, with the ratio of planet to star decreasing as we go along this direction. So what it means, we have also encountered for the size, the differences in the sizes of planets and star. If you want to know the details, I can explain later. But given the different sizes of planets and the SNR that we have introduced. For a high SNR light curves, we are able to predict shape to quite good accuracy, I would say. And another thing that we do is to check what happens if we increase the noise in the light curves. So with the increased noise, we can see that the predictions become less accurate for almost all radius ratios. And this is the limitation for the time being, that for a good SNR light curves, we are predicting very good predictions for the shapes. Okay, so two conclusions is as we decrease the radius ratio of planet to star, the predictions deviate to some extent from the truth value, and prediction map also degrades with decreasing SNR, which is expected. Okay, so another result is just testing it, how the model performs on Kepler light curves. So here I have shown 6 best SNR light curves from the Kepler data, and the prediction maps are shown here. So you can see that most of them are looking very circular, and there's only one that is not that much circular. The question is, if we are able to predict a circular shape for the Kepler light curves for the confirmed planets, then we can say that our model is performing well. On top of this, another very interesting result that I want to show is the prediction map on the exocomet light curve. So what we did is to take the exocomet light curve, which is a fit to the real light curve from Ziba et al., and we have given this light curve simply to this model to see what it predicts. And what you can see is the shape prediction kind of matches with our expectation of what a comet looks like. So this is very fascinating as well as encouraging, and I'll explain why. So another thing, one of the criteria that we have to do is to identify how do we say whether the prediction maps are circle or not. So to do that, we come up with a very simple approach where we take the prediction map, we find out where is the boundary of this emission in some sense, and then just fit a circle to it and find out how much flux is out of this circle versus how much is inside. So for the timing, the criteria that we are using to decide whether something is circle or not is given by this. So for a threshold of 0.95 and a distance deviation of 10%, we are going to call that as a circle. So what do we see, what do we do next is for this particular shape, it's obvious that it is not a circle, and we are getting, this condition is working well to predict that this shape is not a circle. So we take all the Kepler light curves which are above 700, which are in number in 700 with SNR more than 50. And we just see how many of them are predicted as circles or not. So with the condition that we mentioned earlier, around 46% of the Kepler light curves are predicted as circles. And in case we relax this threshold a little, we are getting 78% circles. So what the point of showing this is that even though the Kepler, we have not optimized the model and the training as required by the Kepler data, we are still able to predict with at least half the fraction of planets at circle. So there is a high, of course, we need to improve the model and the parameters according to the data, and especially take care of the noise. But this gives us a hope that this model is, even though it's simplistic, it's going to work as we are expecting it to. So this is my summary slide to say that even with our simplistic convolutional neural network, we are getting very encouraging predictions of the light curves. And even though we have not accounted for the Kepler noise exactly, there are also, you may have thought of the degeneracies which are coming due to various factors, that if you have a shape which is just vertically flipped, will give you the same light curve as the shape which is not flipped. So these are the areas where we have to improve, specifically related to the real data. And the current model is predicting good, giving us good results. So it's very hopeful and encouraging. And we are planning to improve this. We are planning to improve the model as well as by incorporating the Kepler noise itself to see how we can make the predictions better. Along with this, I just want to mention that we also have recently a new postdoc has joined us recently, Isabel, who is also going to continue this work on the test data. So we hope to get interesting predictions and results very soon. So thank you.
Thank you, Deepika. Any questions?
So I have one question regarding the assumption that you take that like along the mid axis, but in the real scenarios, wouldn't be there like many exoplanets which will be transiting away from the let's say the mid axis?
Yeah, there would be, but the thing is that you will not observe them using transit methods. For transits, you need to mostly or most of them will be edge on. Otherwise, you will not see the dip significantly. So that is the reason that we assume the impact parameter to be close to 0. Also with Kepler data, also the impact parameters are not really that high. They are close to 0. So that is why the assumption, I think, is still valid even for real scenarios.
Thank you.
Thanks, Gitika, for that approach for this problem. I'm just curious, is there some specific reason why you are still testing on Kepler data and not test data, which I think is focusing more on the brighter sources? So it would be more convenient, I guess.
No, Kepler is focusing on the fainter.
Yeah, that's what I'm saying. So maybe testing on tests would be more convenient.
Yeah, we are planning to do that. I mentioned that our newly joined member Isabel is going to work on that. I have not. That is the next step. So we have just tested it on Kepler data. We are going to test it on test data and improve the models accordingly to the requirements of individual data sets.
Also, does the noise change between different missions? So like, will you have to work from scratch for different data sets?
Yes, when it comes to noise, yes, we have to understand the noise really well to be really be confident about what we are getting. So, and every mission has its own characteristic noise properties. So we have to account for that in each mission. For the time being, maybe we'll come up with something where noise may be accounted for in some general way, but for the time being, no.
Okay, thanks. That works. Thank you.
Yeah, there's one question here.
Yeah, so other than Dyson disks, what are other anomalies that might reflect, the shape variations or something like that in light curves?
Anything which is not circle would reflect in the prediction maps. So one such example that I gave is an exocomet, which is obviously you can see that even in the light curve, it's a very weird thing. So those weird objects plus even the tiny deviations from a planets are a good, we can't say what they are, but we have to look for at least the anomalous things. Then we can maybe follow up and see what we can do with that.
Yeah, there's one question.
Thank you for the nice talk. Did you try with your simulations of how much higher the SNR needs to be to get a good percentage for the prediction of a circular shape?
Yes. So we For S, we have, so for SNR up to 500, we are getting, up to 200, we are getting good predictions, and the fractions roughly remain the same, little bit here and there. But as we reduce the SNR to below 200, like 100 or even 50, then the predictions are not that well. So there we have to improve now.
Thank you.
Thank you, and let's thank Itika once again. And
Yeah, everyone.
so we are moving on to the next talk, which is an online talk. So we are moving from techno signatures to biosignatures. Linton, are you able to? Can you speak?
Yeah. So can you hear me?
Unfortunately, not able to hear.
Can you hear me now?
Yeah, that's good. That's good. Thank you. And your slide is visible, and you are ready to go. We have 20 minutes, and I'll give a warning by 5 minutes in the message. Thank you.
Thank you. Yeah, so first of all, thank you. Thanks to Jayanta for organizing this SETI session in this workshop, and particularly including an exoplanet talk, which is potentially linked with the search for life in the universe. So today's talk is, I am going to introduce a new frontier, which is essentially how to combine biosignature with technosignature effort to improve the knowledge of search for life in the universe. So I'm Little Mojumdar. I'm primarily based in Niger in Bhubaneswar, where I lead a group on exoplanets and planetary formation, where we ask the questions, how do planets form and evolve? What are exoplanets made of, and how we can observe atmospheres of exoplanet using various facilities such as James Webb, one of the primary example. So I came into the picture for SETI after this workshop, beautiful workshop that we have organized in December in Goa, where we brought together people from astrobiology, exoplanet science, and SETI, and to brainstorm about ideas how to make progress in the areas of search for life in the universe. As you can see from the picture, we have people from astronomy, radio astronomy, infrared astronomy, modelers from exoplanets, and also people coming from the geoscience backgrounds. So it was a fantastic workshop, and which helped to set up, some of the, collaborations, that I'm going to talk about today. So, exoplanets field is relatively new, and it was all started in early 1980s with the observation of first photoplanetary disk, and this disks are the places where potentially exoplanets are born. But the first discovery of exoplanets came around pulsar, which is around 1992. But the discovery of exoplanets around Sun-like star in 1995, which led to the Nobel Prize in 2019. Has created a renaissance for the field. Now exoplanet science is seen as one of the new frontier areas of astronomy and astrophysics, where people are contributing to to understand how common are Earth-like planets around distant stars, whether we can detect Earth-like planets around Sun-like stars, how common are the Earth-like planets in the universe, whether we can detect any signatures for life around planets around other stars, what we can learn about how these planets are formed and how they are different as compared to what we see for Earth. So, and this is obvious because currently we have exoplanet populations where we have detected, more than 6,000 exoplanets as of today. And what I'm showing here, the orbital period with respect to the size of the planet. And as you can see here, large diversity of planets has already been seen, which are, as massive as Jupiter, and also planets like Earth. But there's a new frontier, which is basically the smaller planets, which is the frontier area now, where we have limited data. So the detection of Earth-like planets is still is the area that we are all trying, and this is the new frontier for the next decade. And this is exactly what was the recommendation from astrodecadal, because every decades, National Academy of Sciences from US recommends what are the top priority and what will be the next flagship missions that NASA should lead. So if you look at the recommendations from Astro 2020, then you will see there are two major recommendations. One is we should focus on, identify the area where we can identify habitable Earth-like planets by detecting the atmospheric signatures from them is one of the topmost priority area, along with how this type of planets were formed and how we can achieve this. The main two recommendations were we should build up, extremely large telescopes with, high resolution spectroscopy and high performance adaptive optics, so that we can, we can do direct imaging spectroscopy for, smaller, planets like Earth around distant stars. Along with, we should also build up, a space-based large observatory in the IR, UV, and optical, which will essentially do, direct imaging spectroscopy in the reflected light to, probe some of the atmospheric features which can potentially link to the habitability. And this mission is the next flagship mission after James Webb, which is, Habitable World Observatory. And this will essentially look for, signatures for, habitable planet around, sun-like stars. So having said that, the exoplanets fields are rapidly progressing, and the three main theme for exoplanet science is today, how to understand, if we study exoplanets today, it helps us to understand how they form, how they work, and also we can determine the atmospheric composition for distant planets to get the idea about whether we see some of the features which might be linked with the habitability for this type of planets. And this is why they are very important, because the atmospheres of these planets essentially encodes the information that we need to understand, life. So to tackle this problem, there are two ways to go about it. One is the biosignatures, and another is the technosignatures, because both of them are signatures from the atmospheres. And I will explain what are the key differences and what we can do about them. So the search for extraterrestrial life must proceed for, exoplanet community by looking at the signatures from the atmospheres. Either they will be biosignature or they will be signature related to technology, which is essentially potentially tracing the extraterrestrial life. And we define them as, technosignatures. How we can do that? So when a planet passes in front of the host star, some fraction of the starlight passes through the atmospheres, and depending on the, presence of different molecules in the atmosphere, light get absorbed at different wavelength. And these different absorption features gives you the idea about what type of molecules is present in the atmosphere, and that you can observe and constant using transmission spectroscopy. And this transmission spectroscopy is one of the key techniques that we use to constant atmospheric properties for different classes of planets today. And when you do that, then you get the idea about what is happening in the planet atmospheres. For example, here what I'm showing, typically, if you look at Earth atmosphere also, what we see is, there is atmospheric chemistry happening in the planet atmosphere, and the atmosphere is continuously interacting with the surface, what we have on the surface. So in a typical atmosphere, you see, escaping atmosphere, you see chemistry is happening in the atmosphere, and also atmosphere is continuously interacting with the, surface. For example, if you have a liquid water and you are continuously releasing, steam, and that goes into the atmosphere, and that interacts with the atmosphere, and it forms, different type of molecules, and that we see today using different, remote sensing measurement. So the atmospheres are complex. There is a lot of physics is happening, a lot of chemistry is happening, and that is also one of the reason why we see the effect of the climate and the climate change that we see today. So how we study these atmospheres? Generally, the atmospheres are constant using observations and simultaneously with models. And the modeling is generally done by considering this atmosphere in a simplistic way. Like you can consider the atmospheres in 1D, or you can consider the atmospheres in 3D, and you can predict what is there in the atmosphere. And you can use this model observable to constant what is happening in this, in this type of atmosphere, and whether there are potential signatures that can link with the life in this type of planets. So I'm not going to talk about it, but we have been leading various efforts in this frontier areas on constraining atmospheres of planets around different stars, and how we can measure atmospheric composition. And when you measure atmospheric composition around different planets, how it helps us to understand how these planets form, evolve, and what is the future of this type of planets. So here, I'm just showing you some of the work that we have been doing in our group. We have this in-house model called Nexotrans, which is basically a modeling engine where you can use James Webb Space Telescope observations, and you can constrain what is what is there in the atmosphere, which has been trained using radiative transfer, detailed atmospheric chemistry, and also the observables. And it is also run on machine learning framework as well. And when you have such model which can help you to understand what is there in the atmosphere. So this is the global atmospheric spectra coming from James Webb. So what I'm showing here, from 0.6 to 12 micron, the spectra coming from James Webb, from NIRIS observation, PRISM and MIRI data. And you can clearly see using transmission spectroscopy, you can observe key molecular features from the atmosphere. So such as sodium, potassium, water, CO, CO2, and SO2. So the key idea is, if you have planets and if you use transmission spectroscopy, you can measure atmospheric compositions by using transmission spectroscopy, and you can measure what is the amount for this type of species. And when you know this atmospheric composition, you can understand what is going on inside the planet. So this is the frontier area of the field. So now you have atmospheric gases, but there are also signatures which are potentially linked with the life. So let's talk about the biosignatures. For example, if you look at oxygen and O3, if you look at O2 molecular oxygen for planet Earth is largely related to the photosynthetic process, because if you have in the atmosphere, if you see a lot of oxygen in the atmosphere, that tells you there is ongoing photosynthesis process. And if you have ozone in the atmosphere, that means oxygen is photodissociated because of the incoming radiation, and you form O3. So if you have a planet and if you have an atmosphere where you see a lot of oxygen and O3, then you can certainly think about this is a planet where ongoing going through a photosynthetic process. Then if you look at the methane, which is also one of the gas for planet atmosphere like Earth, where 90% is coming from the biological processes. So if you have methane in the atmosphere, then you can think is also possibly linked with the biological processes. Now, if you have planet where you have both oxygen and methane, and they destroy each other. So you need to have continuous supply of CH4 and O2 from the planet surface in order to build up detectable abundance of CH4 and O2 in an atmosphere. So if you detect CH4, O2, and O3, then there is a possibility you can think about this planet might be Earth-like, and there is and you can constrain some of the processes which potentially linked with the habitability. Along with that, if you look at the near infrared features, for example, you can look at the vegetation rate age, so which is basically tells you there is a lot of vegetations, because all of this vegetation essentially has chlorophyll, and chlorophyll reflect lights in that domain. And this is exactly what we see. For example, if you take the infrared spectrum for Earth, we see a lot of ozone, we see CO2, and we see water. So water representative of, you have the liquid water on the surface, ozone is coming from the molecular oxygen, and you have CO2, which is telling you have atmosphere. But along with, if you have you can also simultaneously look at the features for these molecules, whether these features are broad, that will give you the idea about the surface features also, like whether the planet is susceptible to have water as a liquid form on its surface. Like for example, if you look at Venus, you see a broad CO2 features, which is telling you have much more temperature than what you have for Earth. But for exoplanets, how will you go about it? So for exoplanets, what we do is we look for, we take the, if we really wanted to observe planet in the reflected light, where there is a potential signal for oxygen, O3, along with, other molecular features, you need to see planets in the near infrared UV and optical domain. And how you can do that, you have to image these planets using direct imaging techniques. So these Earth-like smaller planets, they largely orbit around distant stars in a wider orbit. So you need to block out the starlight that is coming from from the star, so that you can see what the planet, and you can constrain the planet composition using direct imaging spectroscopy. So here what I'm showing, a typical reflected light spectra for Earth-like planets from 0.2 to 2 micron, and you can see various features of water, oxygen, and ozone. So if you can detect these features, then you can have the idea whether the surface processes, which is because of the biological activity, can lead to the detectability of this type of features. And if you look at planet Earth from 0.2 to 2 micron, you can clearly see all of these features are present. For Earth, you see beautiful O2, O3, along with you see a Rayleigh scattering slope, and also vegetation, ray range, which is essentially telling you have a lot of vegetations and you have reflected light because of the chlorophylls. So when you are looking for an Earth-like planets around distant stars, we are looking for a planet atmosphere which can replicate, such atmospheric signal. And based on this, we have two instruments. We have two proposals from the community. One is Habitable World Observatory, as I was mentioned, which is for the next decade, where we would like to look for Earth-like planets around Sun-like stars in the from 0.2 to 2 micron. And what you can see in this work that I have done with my student, what we can see various features like oxygen, O3, water, and CO2 can be simultaneously, we can probe using reflected light, using instruments such as HWO, and that can give us a lot of constants, and we can achieve high signal to noise ratio for these detections. Same thing. So there is also another mission which is coming up, which is also a mission concept, which is LIFE, led by European Space Agency. So here we'll be looking for Earth-like planets around Sun-like star, but not in the reflected light. Rather, it will be in the thermal emission. So you are observing the planet thermal emission directly. And for this, we'll be looking at the mid-infrared spectrum. So mid-infrared spectrum essentially goes from 4 to 18.5 micron, and you can clearly see. You could see methane and also the N2O. So this methane and N2O are one, another set of biosignatures that we can potentially probe using, these facilities. So these two instruments, one is HWO and LIFE. This two instrument is tailored to do, search for biosignatures in Earth-like planets around distant stars. And one in the near infrared to optical, and another in the mid infrared, and that will potentially help us to understand and characterize Earth-like planets around Sun-like stars. But biosignature is one way of thinking about habitability. But what about can we look for signatures which is related to technology? If you think about, if you have a planet where already life is already started and it's already civilized, and you want to look for signatures for technology, then what you can do? For here, just look at this figure. So here, what I'm showing the ozone concentration with respect to year. So we know with time, we all know about the ozone hole, right? This ozone hole is created for Earth because of the industrialization and release of a lot of chlorofluorocarbons. So when you release a lot of chlorofluorocarbons, then it goes to the atmosphere and it destroys ozone, which is basically one of the prime reason why we see ozone depletion in our atmosphere. And as you can see, after 1971, there is a drastic fall of ozone in our atmosphere, and then it again shoots up. So this drastic fall in the atmosphere is because this is the time a lot of industry came and a lot of chlorofluorocarbons was released, and we have destroyed so much ozone in the atmosphere. But then Montreal Protocol came into existence in early 1980s, and which is basically one of the environmental act which tells you how to protect ozone in our own atmosphere. So as soon as Montreal Protocol came, various chlorofluorocarbon, release of various chlorofluorocarbon from the industry, was controlled. And as soon as it was controlled, you can see, again, the concentration for ozone was increased. So these chlorofluorocarbons, which are potentially coming from, various industry and, can be thought as one of the potential technosignatures for the atmosphere. And if we can detect this technosignature from the atmosphere of distant planets, then we can correlate them. With habitability as well. And so this is exactly the effort that we have been trying to do. So what I'm showing here, I'm showing a bunch of chlorofluorocarbons, so like CF6, C2F6, and some of the other molecules. Clearly, you can see all of these chlorofluorocarbons has signatures that is available from 2 to 18 micron. That's the region where potentially in the future life will operate. And when you have these features into the atmosphere, then if we record any atmospheric spectrum from the mid-infrared, then you can see whether is there any contributions from any of these chlorofluorocarbon that help you to understand whether this type of planets are this type of technosignatures are potentially present in this type of atmosphere. And this is exactly what Vishal was mentioned. So this work got funded by the Breakthrough Listen Initiative at NICER, and we have now excellent collaboration with Breakthrough Listen. So we'll be hiring a bunch of students will be working on understanding atmospheric technosignatures on exoplanets and possibility of detecting them in the future using instruments such as LIFE and HWO. And this is exactly important because there are so many missions are lined up for exoplanet science, and biosignatures is already a potential target for all of these missions, but technosignature yet to be. So our responsibility is to also see the other part of the habitability, which is like how you can search for habitable planet using technosignature search. And we think future facilities such as Habitable World Observatory Life, and also as an Indian exoplanet community, we have been working on ExoWorld, would help us to understand the search for technosignature on distant planets. And with this, I will end here, and I'm happy to take any questions that audience might have.
Thank you, Little. Questions for Little?
Hey, hello, Little. Vikram here. So, very interesting talk. I wanted to ask your opinion about the DMS and DMDS detection by Madhusudan et al. Paper.
Yeah, so thanks for asking the most difficult questions, but that's great. So the DMS on K218b, I think as a community, we think we need more data in order to see the features for the DMS. And one of the new finding from atmospheric chemistry community is DMS can be produced also by abiotic processes. So not only the biotic process, but you can also form it by abiotic processes. And that's why DMS is also been seen in the interstellar medium. So, so the two things which will help us to understand the search for DMS, one is we need more data to potentially locate multiple bands of DMS. And by the way, for the DMS, the lines that has been used to, the opacity which has been used to detect this molecule is not really high sensitive data. So there is also needs for improvement on the data set, that part. Together with, we need more data so that we can see multiple other bands of DMS using James Webb. And then when you see that, then we need to have models which we should see how much is the relative contributions of DMS coming from abiotic versus biotic, because clearly there are abiotic processes active to form DMS, and whether those abiotic pathways are active, that one is to see. And so this is a challenging problem, but community is up for it. Yeah.
Take one online question. Ramesh?
Yep. Can you hear me?
Yep.
Thanks, Lighton. That's a very interesting presentation. Even though I don't work on this field, I'm primarily a pulsar person. I find that very interesting. maybe my question is sort of peripherally relevant, I should say, because I was at a Pulsar conference recently where some interesting results on first molecular carbon detection in one of the exoplanets, planets around Pulsar, I should say. I know about that Pulsar because it is one of the parts discovery. Just to put in the context, it is like 200 parsec kind of a distance and 1,000th of a solar mass kind of a companion. So that's what we are talking about. So JWST observations had a clear detection of C2 and probably C3 as well. So my question is, obviously, it is probably not a potential candidate for techno signature, I understand. But my question is that most of your targets in the exoplanets category will be much closer. So could you comment on or tell me a little bit about similar sort of attempts have been made on prospective targets? What is the state of the play?
Yeah. So that's a very nice question, and I did talk about it. Let me see. Yeah. So yes. So currently, if you can see here, so the large part of the sample that we have been characterizing using James Webb, the most of these planets are very close to their host stars because they have, some small transiting period because they are observed using transit photometry. So we are probing planets which are hot and very close to their host stars. So now if we define life based on what we know on Earth, then Earth-like planets based on the planet formation theory, and if you want to have water as a liquid form for the primary criteria for habitable planet, then it should orbit a distant stars bit farther away. So as soon as your planet is orbiting farther away, its your transiting period become much longer, and it's not a suitable target for you to do transit spectroscopy. But which is the main target? Which is the main tool for our atmospheric characterization? So for this type of Earth-like planets, you need to do direct imaging. So you need to image these planets by blocking the starlight using a coronagraph, and that's exactly the next flagship mission, Habitable World Observatory, where the Earth-like planets around distant star will be observed using direct imaging, and simultaneously will be doing reflected light spectroscopy, which is the light reflected from the planet, the starlight reflected from the planet to the observer. So that will give you the idea of the atmosphere. So we are not yet there to characterize Earth-like planets using James Webb, but now there is effort. I must say that but you can always look for Earth-like small rocky planets around M dwarfs, because M dwarfs are much cooler, and you can have rocky terrestrial planets orbiting much close to a star with a smaller transiting period, but still you can have a habitability. So this is a new search that's just been initiated, which is basically a legacy survey of characterization of Earth-like planets around M dwarf stars, and to learn. But the results are just beginning to come. So I would say Earth-like planets is extremely difficult around Sun-like stars, but around M dwarfs, we'll see what is waiting for us for the next few years. But we are not yet there to characterize this, Earth-like planets in detail using transmission spectroscopy. Yeah.
Thanks very much.
Yeah.
Thank you. Any other questions? Yeah, there's one.
For the talk. So could you go to the last slide where you showed the spectra for CFC molecules? Yes. Yeah. So is this a simulated spectra, or did you observe in any of the exoplanets?
So these are the simulated spectra. This is not my work. So this is from Ed Sherman. So this is a simulated spectrum by considering different concentration of CFC. So what you can see here. So the you have a black line is Earth-like planet atmosphere. Okay. And this is the thermal emission spectrum from Earth-like planet, the black line, without considering any technosignature gas. Now, if you assume, but clearly when you have that, you can clearly see there is a ozone features, there is a water features, and there is also CO2 features. So now you are assuming if that particular planet is is a good target for your technosignature search, and you are assuming you have 1 ppm, 10 ppm, 100 ppm of chlorofluorocarbons, how does your spectra changes, right? So each of these different color representative of your Earth-like planet with technosignature gases with different concentration. But we don't know any of this, whether what will be the concentration for these chlorofluorocarbons, right? So this is just a model prediction. So if you have Earth-like planets, a template spectrum, and now if you assume different concentration of technosignature gases, then you clearly see differences. Now the question is whether these differences are sufficient enough to be resolved by future observatories. So that was the main target for this paper that Ed Schwartman has shown. So these are all simulated spectrum.
Thank you.
So I have one question.
Yeah, please.
Anyone produce a spectrum of the Earth from far away satellite on similar wavelengths, and how do they come back?
Oh, so
how Earth looks from the farthest spacecraft, the spectrum of Earth?
So basically, are you asking? Let me understand. So are you asking how Earth-like planet around other?
Not Earth-like, Earth spectrum of Earth.
How it differs as compared to our Earth, right?
These lines look from a faraway spacecraft.
Oh, okay. So you are asking if we observe Earth from other spacecraft, right? Yeah. Okay. So there is an effort on that. So basically, observing Earth as an exoplanet, right? So even if you look at Chandrayaan has a payload where Chandrayaan-3 has a payload which is basically SAFE instrument that wanted to look Earth using polarimetry. So you from moon surface, you were trying to observe Earth signal using polarimetry, right? So there are efforts. People are trying to observe transmission spectrum for Earth using a distance spacecraft, of course, and the constraints that we have currently, for example, the constant that we have. Like we have, if I'm not wrong, we have some measurements from epoxy. Epoxy has some of the measurements, and it gives you the good constant on what you have in the atmosphere if you measure with the local radiation sensing measurement. So we have some measurements, but not much. But this is also another topic that people are started, integrating in the community, observing Earth as an exoplanet from using other instruments.
Thank you. It's interesting. Any other questions before we have to break for lunch? And if not, let's thank our remote speaker, and you can always get in touch with him.
Thank you.
Thank you. Thank you. Thanks again. And we are going to be back with a short lunch break, 2:10, the next session.